Okay, so we can kill this. We can minimize that and get that out of the way since we got the top hat code. Okay, so hopefully everyone was able to get the homework in and it wasn't too much of a freak out. The next homework set is up, and then there will be one more before the midterm that will be posted this Friday, provided I get through what I wanted to get through today and tomorrow, which I should be able to. And then I'll post the homework, the one last homework set for Friday, on Friday, and then that will actually be the end of solidification. I've decided will be the last of the material on the exam, so that you'll have a little bit of time to process that without worrying about new stuff. And remember, the take home, the exam will be take home. Okay, so we started talking on Monday about alloy solidification, right? And the important thing is to remember is that there's a solidification range, right? That falls between, for a given composition, the liquidus temperature and the solidus temperature, right? And that is the freezing range, and that the composition is not going to be constant, right? But that the first solid that forms is going to be here, and the last solid that forms is going to be here, and the last liquid to freeze out is going to have a composition over here. And we can define the concentration of the solid divided by the composition of the liquid here as some constant, which is our partition coefficient. No, the exam is the 21st. I'm just saying that the material that I get up to Friday will be the last material on the exam.
Quick question about this diagram here.
Yeah.
I was doing the reading, and I might have a bit of a brain fart here, but you have the composition of the solid and the composition of the liquid at that certain temperature, right?
Mm-hmm.
What is this middle range? Like, what is in the vat? Is that just like a
this
amorphous area? Or?
In between?
Yes.
Right, you're in the two-phase region, right? So that means you have a mixture of solid that's already solidified and liquid that still hasn't frozen yet. Right?
That's pretty similar. I don't know how I kind of got confused on it.
Yeah. So out here, this is complete liquid, right? Out in here, this is complete solid, right? This is our alpha, right? Down here, this is a eutectic, right? So this is going to be alpha plus beta. The beta phase is way out here. That's cut off in this diagram. We're only considering about freezing down into alpha, right? So here we have a mix of solid and liquid in equilibrium. Right? If we hold our temperature constant, we're not going to get rid of all the solid or all the liquid, right? The solid and the liquid are going to have two different compositions. The solid is going to have a composition that's dictated by the solidus line, and the liquid's going to have a composition that's dictated by the liquidus line, right? So, you know, thanks for speaking up there, right? Because phase diagrams are completely central to everything that we do, both in material science and welding, right? You have to understand what's going to form. And so reading them, right? So there's going to be lots of phase diagram questions in homework and exams. So if you're uncertain about them, now is the time to start reviewing and ask ask questions, right? So if we think about solidifying down this line, right, we're all liquid until we hit the liquidus line, right? Then we're going to nucleate some solid, and the first solid that forms is going to have this composition out here, which is our partition coefficient times our alloy composition, X naught. Right? And as we cool down, both the solid and the liquid get more concentrated in solute. And if we do this at equilibrium solidification, the last solid to form has our alloy composite, has our alloy composition, and the last liquid to form, the last liquid to freeze, I mean, is going to have composition X naught by K. Right? So make sure that that process makes sense to you. Right? And because we're idealizing this phase diagram, and these are straight lines, right? They're straight lines with different slope. But the distance between the solidus and the liquidus line as you go down in temperature increases by the same amount as we go down, so that this ratio always works out. Right? And so that's kind of an important concept, right? If these were, in the general case, curved, this partition coefficient's only approximate. We you know, but for understanding things conceptually and from a theoretical point of view, this idealized picture works just fine, right? Because for the most part, we can always draw, even if we have curved lines, around the freezing temperature of our composition, right? We can always approximate those curved lines by straight lines, and have this sort of work out, right? So we're talking here about unidirectional solidification, right? We're saying, let's consider equilibrium solidification, right? So equilibrium solidification means infinitely slow. So that means we have time for diffusion to happen in the solid and in the liquid, so that the composition of the solid is always going to be homogeneous, and the composition is always going to be homogeneous. And the composition is given by the solid and the liquidus temperature for a given temperature. And because we need to follow conservation of mass, in this case, we're not destroying or creating any solute. There's no atomic reactions that are happening here. That any solute that is rejected from the solid as it freezes has to mean an increase in composition of the liquid, right? And so that means these areas have to balance. The area of these two rectangles has to be identical.
So the idea here is that the liquid can, for lack of a better term, absorb the solute at the same rate the solid rejects it?
Yes, so if we're doing this very slowly, there's lots of time for this to happen, right? If we do this more quickly, which is what we'll talk about in the next examples, then there may not be time, right? Especially in the solid, because diffusion in the solid is slow, right? So we'll work through three cases. So I left off on Monday with talking about sort of infinitely slow equilibrium solidification. Then we're going to talk about solidification where there's no diffusion in the solid and perfect mixing, right? And this is a really good theoretical case study to think about. This is where we'll get our Scheil equations that allow us to think about this system. And then we have solidification with no diffusion in the solid and diffusional mixing in the liquid. And we need to consider this to get at dendritic growth or interface instabilities, right? Beyond this, there's an infinite number of ways that solidification can happen. And we're not going to worry about each and every sort of case. Thinking about these three sort of cases allows you to make reasonable assumptions and reasonable predictions almost all the time, right? Okay, so if we think about what happens during equilibrium solidification, I'm going to say it again, this is review, right? We start at X naught, we cool down until we hit the liquidus line. Then the first solid that forms is going to have a composition here, given by our partition coefficient K times our alloy composition, right? The remainder of our liquid, right, because this is an infinitesimally small nucleus compared to the size of the bar, right? The rest of the liquid still has composition X naught. As we freeze, the composition at the interface is always dictated by the solidus line. So the next bit to freeze is going to be slightly richer in solute than the first bit that freezes. And now we have a composition gradient. So when we have a composition gradient, you learned in 2010 in thermodynamics, that means we have a chemical potential gradient, so we're going to have diffusion. So given time, the composition in our bar will equilibrate, will become constant, right? And in the next topic, diffusion, we'll talk about how long that takes to happen and, right? And all of that. But if we're doing this very, very, very slowly, there's always time for this composition gradient to work itself out. So the bar is uniform, but then the next tiny little sliver that freezes is going to be slightly higher than the composition out here. The next little bit of liquid that freezes is going to be slightly more dilute than the remaining liquid, right? And eventually we will freeze out and everything will be nice and uniform. We'll have the last bit of liquid will have this composition to freeze. Once it will slowly sort of freeze, diffusion will happen, and will equilibrate, right? There's kind of like a Zeno's paradox that can happen here, right? You say I can diffuse so much liquid away. It's kind of like walking to the wall. Each step, if you only go halfway to the wall in a given amount of time, you'll never, by that argument, you should never get to the wall. It's the same way here, right? We have a finite diffusion rate and we're getting liquid that's more and more and more concentrated, right? So essentially, if we didn't do this infinitely slowly, our composition would build up in the liquid and we would end up with a eutectic composition out here, right? Which we'll see in the next thing. But here we're saying diffusion, we have enough time that everything diffuses and everything stays. There's always a step function in composition at the interface, but it's always homogeneous before and after the interface. Okay? The next case is now we have no diffusion in the solid, but we have perfect mixing in the liquid, right? And so that mixing comes from convection and diffusion. But we're saying that there's not enough time for diffusion to happen in the liquid. So the composition of the solid remains the same as when it froze, but the liquid is always homogeneous, right? So that means that the composition of the solid is going to vary spatially. The first solid is going to have the composition of kx naught. If we just went down our curve, we would say that the last liquid is the last solid that freezes in equilibrium solidification had composition x naught. But in reality here, because we don't have any diffusion, it means that the last liquid that's going to freeze is going to have composition x naught by k. Right? So the first solid will always be more pure than the mixture as solid is rejected into the liquid, right? And as our solidification progresses, the liquid becomes more and more concentrated. What we have to remember is that at the interface, we still have local equilibrium, right? We still have the interface composition and temperature still have to be related to each other, right? And because, and we'll explain what this means in a figure, and because the first solid that freezes out is less than our alloy composition, that means the average composition of the solid is going to be less than the composition at the interface. Right? I'll explain what that means in a little bit as we go on. So we begin essentially the same, right? We're going to cool down, we hit T1, we start to solidify at this point, Kx naught, right? So now we have this composition. As we drop our temperature, as we cool down, right, our solid composition is going to follow this line, right? So that means what we're going to have is a gradient in composition in our solid, right? And our average, so the average of Kx naught and Xs is going to be some line in between here. So our average composition of the solid is less than the solid that's currently freezing, right? So this is the average composition of our solid as we move down, right?
What was the previous one we saw?
This?
Yeah.
This is just the initial. This is just as it first starts to freeze, right? So there's still a gradient here, but it's just, there's not enough length for you to really see it. Okay? Right? So now what's going to happen? Right? We keep going down and down as we keep lowering our so actually let me ask a question, right? So I keep saying as the temperature drops, but why is it necessary to drop the temperature to keep freezing from to keep solidification happening? Well, first there's just the heat flow of it, right? We've got a temperature gradient, right? And things are naturally cooling down, right? So there's that to contend with. But also, if we kept it at a constant temperature, so if we kept it at T2, we would be at a point where we have solid and liquid in equilibrium, right? And so to make any more solid form, we have to drop the temperature. So if we want to solidify out this whole bar, we have to go from above the liquidus temperature to below the solidus temperature. Right? And as we drop the temperature and the composition changes, the freezing point. Oh, I just saw that. So, yeah, so salt water, so from the chat, salt water does the same thing, right? As you freeze, the brine becomes more concentrated. And the solid is more and more pure. Or, well, not more and more pure, but the solid that forms is less briny than the liquid that remains. Right? That's fractional freezing distillation is one way of thinking about that. Right? So in order to keep solidifying, we have to keep, the temperature has to go down, right, in an alloy, because it's not like we have a single freezing point. We have a range over which the two phase, the liquid and solid together, are stable, right? So as we keep going down, the composition of our liquid gets more and more concentrated, right? But local equilibrium always has to hold at the interface, right? So as I move down, eventually I get to this point here, T3, where my solid is the same composition as my initial alloy, and my liquid composition is way out here, right? But local equilibrium still holds at the interface, right? So now I have to think about freezing out a liquid that's more concentrated than it was, you know, initially, right? And because we don't have any diffusion, this area here needs to match another area over here. So that means the composition of my liquid is now above my alloy composition. So that means to keep freezing, the composition of my solid also has to go above my alloy composition. And that keeps going until I reach the eutectic composition. And the last bit of liquid that freezes out at my eutectic into alpha and beta, right? So even though I'm single phase here, when I hit my eutectic here, even though my average alloy composition should freeze into the single phase region, I actually freeze into this eutectic region and now have a two-phase mixture out here at the end of my bar. All right? So this theory is actually really, it's important for metallurgists and welders, right? Because what this tells you is that if you think about for a weld pool, if you do a spot, right, you're going to have a composition gradient of your, if you're using a filler metal, right, you're going to have a composition gradient not just in the spot that was melted and mixed, but you're going to have a composition gradient within the melt pool, right? So after you solidify, the composition of your melt region is not going to be homogeneous. So you're going to have a compositional gradients across your heat affected zone due to diffusion and other things, but you're also going to have another composition gradient in your solidified region, right? This is also really important for functional material people, right? This idea of solute rejection from the solid into the liquid is how purified, high purity materials were made for the early semiconductor devices, right? We'll talk about the concept of zone refining next week. Right, which is was invented at Bell Labs about the same time as the transistor, but the patent on zone refining made Bell Labs a heck of a lot more money than the patent on the transistor did, because in order to fuel the demand for solid state devices, the people needed to be able to make very high purity silicon and germanium, right? And zone refining was how they did that, right? We'll talk about it in detail, but it's all built on this idea that the first solid that freezes is going to be more pure than the average composition, right? So maybe start, thinking about this here. Okay. So if we have a eutectic system, conservation of mass is going to dictate that the last drop of liquid will always be at the eutectic composition, right? If we don't have a eutectic, right, what essentially this says is that this composition curve will asymptotically go up until we hit near pure B on the other side, right? We just need to maintain this mass balance, right? But if we have a eutectic in our phase diagram, we're going to go up until we hit the eutectic composition, and then the remaining is going to freeze out, right? So that means if we have a directionally solidified, right? So even if we don't have a directionally solidified material, what this means is that after we do casting, if we want the part that we cast to have a uniform composition and uniform properties, it means we need to do a diffusional heat treatment. We're going to need to hold this at some temperature below the eutectic point, the eutectic temperature, right? So if we look at our phase diagram, the eutectic is going to have the lowest melting temperature. So we're going to have to hold this at some value that's close to here, as hot as possible, and allow the solute to diffuse, to homogenize the composition in our part, right? So this happens in steel plants, steel mills every day, right? And this was the advent for concepts like continuous casting that we'll talk about in a bit, okay? The key thing to realize is that no matter how dilute our initial alloy, the last little bit that freezes is going to be pretty concentrated, right? It can be a very small amount of volume, but the last bit that freezes is going to be fairly concentrated in our solute, right? This is just a really critical idea, right? So Nathan, I'm not sure I understand your question, right? Is that because of delta G?
It requires a lower and lower freezing point.
Yeah.
Is that because it requires more energy, more of a desire to drop that?
Well, so there's a couple things, right? So the latent heat of fusion is going to depend on the composition, right? Because the energy of the Gibbs free energy of the solid and the liquid are going to be different, right? So that drop is going to be different. We also have a changing delta G of uh, mixing, because the bonds in the liquid are different than the bonds in the solid, right? And all of this sort of comes together, right? But really, it gets a little tricky when you try and go back from the phase diagram to thinking about how the individual Gibbs free energies are changing, right? So I think until you really sort of begin to internalize all this stuff and think about it a lot, it's really easiest just to think this is the composition here. These are the compositions that are given by the common tangents, right? Which these are the compositions where our chemical potential of each element is going to be the same in both the solid and the liquid phase, right? So I think it makes more sense to think about these are the compositions that give you the balance of chemical potential that you need to maintain equilibrium, right? So again, this is kind of, I understand that this is kind of an abstract idea, right? You're not used to thinking about materials in necessarily this dynamic way, right? And in thermo, everything was done, everything is equilibrium. Everything is really slow, right? And now we're thinking about a case where I would say we have para-equilibrium, right? We always have to have local, highly localized equilibrium at that interface. But the rest of our system is changing. The composition of our solid changes with space and time, and the composition of our liquid changes with space and time. So it's a little bit difficult, right, to think about the first time. So you know, you're gonna have to you know, you've read this, you're probably confused. Watch the lecture, you're going to be confused. Read the material again, work on the homework problems, and slowly the confusion will lessen. I promise, right? But these are not immediately easy concepts to grasp. And I'm going to try and make them as straightforward as possible, but there's just a lot of things happening here. Okay. So if we think again about conservation of mass or solute, right, we're going to think about what happens as we freeze out, right? So the change, this is from a different source. So we can replace, this uses C for composition instead of X for mole fraction. But the concept is exactly the same. And I wish there was this picture in your book. But as we solidify, we have to change composition from the liquid to the solid, right? And we're moving our interface over a tiny little amount. So this is the fraction, the tiny increment in the fraction that's solidified, right? And so this whole big rectangle, this length here, this is the fraction of our solid that's frozen. And from the interface to the end of the bar is the fraction of our liquid, right? So we're adding a tiny little bit of solid, we're removing a tiny little bit of liquid, and for mass balance to hold, that means the composition of our liquid has to increase just a tiny little bit, right? And so what that means is the area of these two rectangles has to be the same, right? And by equating the area of these two rectangles as we move our interface over, we can define what we call Scheil solidification, right? And we can use this to predict the compositions as we move on. This is also called the non-equilibrium lever rule, right? Is another word for these Scheil equations, right? So the solute that is rejected into the liquid has to balance the composition change in the liquid, right? So this is just a mass balance, right? And we define our composition, our partition coefficient as the composition of the solid over the composition of the liquid, right? And the fraction that has solidified of the solid and the fraction that's of the liquid, these have to equal 1. So we can plug these in, and we get this differential equation here, right? Right. This is just nothing but a fancy way of writing the conservation of mass, right? Then we also know we have the boundary condition that when we initially started, the composition of the liquid has to equal our alloy composition when the fraction of the solid equals 0. Right? So this is a boundary condition or an initial condition that we can use to solve this PDE, right? So we can rearrange and we can integrate from, this is our differential of the fraction of the solid. So we're going to integrate this from no solid to where we currently are. And then we can integrate the composition of the liquid from our initial alloy composition to the current composition of the liquid, right? And when we do this, this gives us our Scheil equations, right? Which basically says that we can always find the composition of the liquid is equal to our average alloy composition times the fraction of our liquid that's frozen raised to our partition coefficient minus 1 power. Right, and the same thing, we get this expression that gives us the composition of the solid, right? So this here is essentially how we can predict these curves. These composition curves, right? And for homework, you will make some plots as you plot this out, right? So, and you'll see you get things that
What is
look like
the
this.
F again?
F is the fraction of the solid. Like the fraction that's frozen. If the whole bar has length 1.
So this is about like phase, not composition.
Not composition. This is just what percentage of my bar is solid and what percentage of my bar is liquid. Right? Or how far along the length of my bar is this interface? Right? So if I have a bar that's 1 meter long, when I've frozen out 25 centimeters, right, my FS is 0.25 and my FL is 0.75. All right. So this is a really, really useful set of equations. And if you remember back in the first lecture, I said there's a couple things that I expect you to remember, right? This is one of them, right? So if you remember these Scheil equations, right? If this is like one of the very few things you remember from this class, you might not remember exactly how they're derived, but you know their general form, I'll consider it a win, right? Because these are super useful. Okay? So now let's think of the third case. Before we assumed that we have perfect mixing in the liquid. Now we're going to say we have mixing isn't instantaneous in the liquid. We don't have perfect mixing, but we're going to have some diffusion. As we reject solute from the solid into the liquid, as it freezes, it means we get a pileup, right? We end up with a liquid that's more concentrated near the interface than far away, right? And I know we haven't talked about diffusion yet, but I've made that sort of a choice in how I presented it. But this, we can just say this pileup region is going to have some characteristic width. And if we conceptually think about what goes into that characteristic width, it's going to depend on two things, right? How fast the interface is moving, right? Because the faster the interface moves, the more solute is getting rejected into the liquid, right? And so if we're rejecting solute faster, we're building it up faster. And that's going to be balanced by how fast we can diffuse it away, right? So the measure of how fast something diffuses is the diffusivity coefficient, D, right? This is, you talked a little bit about diffusion in 2010 and probably in thermodynamics. Did Professor Akbar talk about diffusion at all? I'm getting silent, so I guess that means no. Okay, so, but anyway, so we're just, this is like the diffusivity for now, just think of it as this is like your heat conduction coefficient, right? It just tells you how fast I can move solute through the liquid. So the width of this pileup out front of my interface, or this concentrated region out front of my interface, is going to be given by this ratio between how fast the interface is moving and how fast I can diffuse the solid away, or diffuse the solute away, not the solid away, the solute away, right? So the width of this pileup region is given by this ratio. So if we think about what happens here, it starts out exactly the same as our previous case. We're going to start freezing out at Kx0. But because we don't have perfect mixing, we get this pileup of composition here, of solute here. And eventually that's going to reach our liquidus line, or go back to our phase diagram. Right. Right, is our X0, right? If this is our alloy composition, right? We start out here, our liquidus, we're going to pile up really quickly in front of that interface until we reach this point here. And when we reach this point here, composition in our liquid, local equilibrium states that our solid composition should be X naught, right? And essentially this is where we hit a balance. We hit a steady state. So we're going to hit this steady state region where our solid stays at the composition X naught, and our liquid is going to stay at a composition X naught over K, right? And we move along until we reach the end where there's essentially no more room when the remaining length of our bar is less than the width of this pileup region, right? Then we get a sharp transient increase and freeze out at our eutectic composition, right? So the key differences between the previous case where we considered perfect mixing and this case is that in the liquid far away from the interface, our composition is still our average alloy composition. So far away from the interface, we're at X naught in the liquid. The only region where we have this increased composition is right in front of our moving interface, right? And so that's why in the case of perfect mixing, right, our solute ended up going above our average composition earlier, right? Because our whole liquid is assumed to have the same composition, right? Whereas here, our whole liquid, most of our liquid still has the average alloy composition, and it's only the region right in front of the interface that has an elevated composition, right? And this region of elevated composition, the length of this has to do with the velocity and the diffusion, right? But the rest of this out here doesn't know that there's freezing happening. It doesn't know that there's an elevated composition here.
So A is equilibrium, B is the rapid cooling?
No, this is still assuming only diffusional mixing in the liquid, but A here is at the early stages, right?
All right, and
so
B is,
before the liquid, the composition of the liquid right in front of the interface, before it gets to X naught over K.
Got it.
Right? Then once it does reach X naught over K, we enter this steady state regime.
So what is it right now, the composition in A?
In composition in A, well, X naught over K is somewhere up here. Right? So it's less. Right? But the important thing to get about this is that we get this pile up region, we get a region of steady state solidification, and then at the end we have this final transient, right? And this now sets up our case for dendritic solidification or an unstable equilibrium. So we'll go over that on Friday, and then I guess Monday will be the last material that's going to be covered on the final exam. I thought I would get a little farther than this today, right?
You mean the midterm?
For the midterm, yeah, I'm sorry. Right? Right.
Wait,
I mean, unless
so
you guys...
The midterm, so the midterm's not to the 21st.
The midterm's not to the 21st, but I want to give you guys plenty of time to work on the homework and get homeworks back and go through the solutions for the homework that are going to be posted very soon.
Excellent. And
right? So that you just have more time to prepare for the midterm. Right? And I'll do the same thing sort of on on the final, right? We'll say the last little bit of class before the final will be stuff that I think is cool and we'll talk about, but it's not necessarily going to be stuff that's examinable, right? Right. So the last like 4 lectures or so or something like that won't be on the final exam, right? Again, it's just more that I want to make sure that you guys have time to prepare. You know, in review, because, you know, there's just a lot of new material, right? So I don't want you guys to feel overly rushed. So Joel, like ice cream. What's like ice cream? Okay, well, material, oh, that will be covered, but not on the exam. So I still don't completely understand, but sure. The ice cream on the cake, you mean? Is that the same? Is that the bonus content? Yep. So, okay. So I'm going to stop there. Friday, we're going to talk about dendritic solidification and zone refining. And we're going to have to, I'm going to review this at the beginning because dendritic solidification depends strongly on these composition gradients and the temperature gradients that are associated with this. So Friday, we'll start by reviewing this diffusional mixing in the liquid again. Okay? Until then.
Before you go.
Oh, sure.
So I'm just trying to make sure I understand these figures. So A is the compositional gradient basically right when it starts solidifying, correct?
Yep.
B is shows the gradients after it's been going on for a while and until it managed to reach X over K, which would be at temperature equals what?
In this case, your phase diagram, right? It would be, where's the exact one? It's T3, right?
Okay, I've got that from the reading. That's fine.
Right? So if this is X naughts our alloy composition, right?
Mm-hmm.
Essentially, in the steady state regime, we're in this is our local equilibrium. The liquid is at this composition and the solid is at our alloy composition.
So I understand those first two pretty well. Can you explain the third to me a little more?
Okay, so we still have to have mass balance, right? So we have a steady state regime until the amount of liquid that we have left at the end of this bar is less than the pileup length. Right? So you can imagine moving this out, right? And as this slope here reaches the end of the bar, now the average composition, the composition of our liquid has to keep increasing to keep our mass balance. And it will keep increasing until it hits the eutectic composition and then freezes out.
Got it.
Right? So this last bit here is exactly the same as this last bit in the perfect mixing case.
Okay.
Okay? Right? And it just has to do with when does this pile up reach here? The end of our bar. Because we're not going to lose solute to the vapor, right? It has to stay in the liquid.
Yeah, we're cooling, not heating.
We're cooling, not heating, right? So that's where this is coming from. So everything until the end of solidification will be covered on the exam. Right? So there may be there'll be a little bit of stuff from Monday that will be on there. Okay? So have a good one, everybody. And we'll see you Friday.